So thank you all, as Cindy mentioned, thank you all for joining us today. Today's presentation is going to be on Linux tools for text processing. The slides for today, as well as all the slides for all our complex webinars, can be found at that bit.ly link that's provided below. In addition to the slides, we also have some supplemental material like exercises. You can find those that are directly related to this presentation in the GitHub. That first GitHub link. In addition, the gentleman who curated this particular set of slides, Bob Sinkovitz, also has a Coursera course, and so he has some additional supplemental material available for you at that last link there. As Cindy mentioned, my name is Nicole Wolter. I am part of the Data-Enabled Scientific Computing group here at the San Diego Supercomputer Center at UCSD. And today I am wearing my complex team hat. So if you haven't joined us before, just a little bit about complex. Complex is an NSF training award. We are now in our third year, and we really focus on helping users to be more efficient using the system. We kind of focus on people who are just getting started with HPC, and that transition from desktop to HPC systems, or people who have been on the system for a while now but just want to learn to do things a little bit more efficiently. So for the next hour, I will entertain you with Linux tools. They're also sometimes named commands or utilities. I might use them interchanged the way I mention them. But we're going to start out with a little bit of an introduction. We will provide why we decided that this was an important topic to have as part of the complex series. Then I'm going to segue a little bit and talk about the Unix philosophy behind it and the people who developed the tools and basically the philosophy behind that. Then we'll spend the majority of our time talking about some of the Linux tools we have. So this list of tools is actually not random. Unix has about 100 to 150 commands or utilities out there. There's this big range because depending on the flavor of Linux or Unix that you're using, it can range. And of those, there's about 25 to 35 specifically text processing utilities. So the tools we chose to present here cover kind of the core operations that you'll need to do to manipulate data, curate data, evaluate data. So we'll cover things like searching, filtering, sorting, character manipulation, do some previewing and counting. After we go through all these, I'll kind of tie it all together by sharing with you some case studies of how we here at the center have used these specific tools in our daily workflows. I'll talk briefly about taking advantage of LLMs, and then we'll finish up and we'll open it up for questions and stuff. As Cindy mentioned, please feel free to put any questions into the chat as we go along. We have some other complex team members here who can address them, and then we can also address them at the end of the talk. So you all came here with some specific intent in mind, but I also wanted to give you kind of a little bit of perspective of why we thought this was such an important topic to have in our complex training, in our training material. So in today's day and age, we are inundated with data. Both we have raw data, which we need to manipulate and curate and use and put into applications to extract information out of them. And we also can create lots of data and output files from that data. So what this session is really about is being able to use the native tools on a Unix system to manipulate that data in the grand scheme. So post-process and doing pre-processing through them. As we go through the tools, and maybe when you looked at them first, you saw the titles, and they're kind of very self-explanatory of what these tools do. And say, well, you know what, I can already do all these things. So what makes this again, why we think this is important is being able to do these things natively on the system. So of all the HPC systems out there, they are all generally Unix-based operating systems. If you are used to using a desktop system, it takes time to move files off, do whatever data manipulation you need to do, and then move them back on the system. So we want to make it so that your workflow is more efficient. Also, with the amount of data that is out there, you could be working with hundreds of files versus one file. So being able to script this, all the tools that we're using today can be scripted and put in bash scripts. I'm not going to talk too much about that today because as you saw in Cindy's pre-slides, we do have a full session on bash scripting. So again, the goal here is to make your work quicker, ensure that you don't have to do anything tedious. And the last thing is because it can be scripted, you can document whatever you do to these data files so you can avoid creating errors in your workflow. So Linux has been around for a really long time and it's still a really great operating system. Back in 1976, there was a report written and the authors kind of laid out what the philosophy was behind behind the tools that they were going to use. So there's kind of three things that I want to pull out or draw your attention to. So the first thing is make each program do one thing well. So very often in today's lives, we get tools that do just about everything you throw in the kitchen sink, but they all do all the things kind of meh. So the goal here is, again, to do one thing very well. It's not to say that there's not a lot of options so that you can customize and kind of modify how that tool does it. But if you're going to sort, you are only going to sort data. You can sort it in reverse. You can sort it by different fields, but it's only going to sort. But to accommodate for this, the second thing that I want to draw your attention to is that the theory behind expect the output of every program to become the input of yet another as of yet unknown program. So basically, each individual tool does its one thing well, but you can string all the individual tools that do their one thing well to do lots of things really well. And the last thing that I want to draw your attention to is, as we are an evolved species, we should really take advantage of tools when we have them. So with that, I'll start and talk about the tools that we have here today. So the first tool I'm going to talk about is find. And as the name kind of insinuates, find is we're looking to find stuff. Specifically, we're looking to find files. So the find command is going to search for files. It can search for files based on the name or a name, the type of file that, the types of files that there are. It can search for size of files. It can change for modification times on files. It can change, search based on permissions or ownerships. And what this does, so in this example here, it will search an entire directory recursively. So that means so when you're searching, you never have to open a file to find out what's in there or go down in different directory structures to find files. You can search recursively all the way down. So in the first example we have here, we use the find command and the dot. So the dot in Unix indicates that from this particular directory. The dash name is indicating that I'm looking for a name specifically. And then after that, it gives a kind of a wildcard. The star means anything plus the .txt. Unix is very particular to, or is very case sensitive. So if you say lowercase txt, it is only going to look for files with lowercase txt. If you want to look for files that have upper and lowercase mixed, you can use the second command we have there on the bottom left, which is the iname. Including the -i makes the search case insensitive. But again, that means that the T can be capitalized, the X can be capitalized, or the other T can be capitalized. There are other ways that we can use things using regular expressions, but for this, we're going to stick with just kind of the high level, what we can do. In addition, the find will allow you to take some actions based on that find. So the two big ones are that you can search and you can delete the files that you find. You can also execute commands on files that you find. Now, why might this be interesting? Something that's very common in these HPC shared systems is that because they're shared and because they have specific resources that are limited and they have different file systems, the file systems will have different quotas on it and different file retention policies on them. So if you happen to be in the home directory, here at SDSC, we limit the home directory to 100 gigs. Once you reach that limit, you can't write anymore to that file. So a nice way to identify files that you could clean up very easily would be to use the find and the TMP. So TMP kind of is temporary file. And so it would indicate that this is not an important file. So you can find all the files in the directory that are TMP and delete them. And so this is a really quick one-liner. Similarly, if you don't want to delete those files, because they are very important, so log files might be important for reports later on, you can search for all the files that have log, and then you can execute some commands on it. In this example, you can zip them up so that you can move them to a different location and store them for later on. By default, the find will just print the line, just print the file names that it has. You can also like hard code and say .print, but even if you leave the print off, it's going to do that for you. The next tools we're going to talk about are head and tail. So head and tail are commands that are going to allow you to preview parts of a file without opening them. So this is often very nice because we can search hundreds of files without opening. Opening a file takes a couple of keystrokes, and opening and closing takes time. So when might this be useful? For input files, very often the top lines in an input file will indicate what is actually in that file. So it can say when it was created. Perhaps it has a header file, so it shows you the format of what you're going to see in there. Similarly, for tail files and output files, usually if you get results or if you get errors, it's going to show up at the very tail of it. By default, the head and tail commands are going to output either the first 10 for the head command or the last 10 for the tail command. As you can imagine, sometimes you don't want 10 lines, so it does give you the option that you can change the number of lines that it's going to return to you. So in this case, we use the -n, which is number of lines, and 7, and so it returns just the first 7, and again for tail, the last 7. In some cases, we know that our files have information that is garbage, but we want to have everything else in those files. So let's say there's legalese that says, that every file will have the same thing. This file was created by so-and-so, and we are not interested in that. So we can specify all but the last number of lines or all but the first number of lines using this. So for the head command, you do n minus 15. So you're showing everything but the last 15 lines. Similarly, tail -n plus 16 means everything after the first 16 lines. The next tool I'm going to talk about is paste. So the paste command merges lines from multiple files in a side-by-side fashion. There's other tools that kind of merge files together. Cat will stack them vertically. What is nice, whereas, I'm sorry, paste is going to merge them horizontally, and it'll join those corresponding lines with the delimiter. By default, it's going to use the tab. So here an example, we have the fruits.txt file, so it just has apple, grape, banana, and a second file is colors, red, yellow, purple. If we paste those two together, we can see their they are now in columns. Things to note, you don't always have to have the same number of rows for them to merge. You can also specify if you want to have a different delimiter. By default, again, it's just it's a tab, but in many, if you're creating input files for other applications, it might be specific how it's going to expect that input file. So in this case, if you're expecting a comma, you can use the -d that stands for delimiter, and in the single quotes, you can do a comma. Thing to note is that you could actually also change what the delimiter is for various columns. So if in those single quotes you put different delimiters for each, it will use each delimiter for one delimiter going forward. Next tool I'm going to talk about is NL, which stands for number of lines. So the NL command is a really flexible. It's different. So there's other tools you can use to add numbers to a lines. We'll talk a little bit later about the sequence. So at the very bottom of this page, you can see the sequence command. We can use a word count -L, which counts the words or counts the number of lines there are in a file. And then then we can paste the number of the line number plus the column. We can also use awk, which we'll explain later, but again, these are a little more involved. The simplest way is to use the cat command. The cat command is very simplistic, and it just adds a number to every single line. So what is unique about NL is that it understands the concept like logical pages, headers, footers, blank line handling. It also lets you choose whether to number all those lines or not. You can specify you only want to number lines that are not blank, or you want to just number certain sections. It also lets you customize the numbering styles. You can do right aligned or left aligned. You can also specify where you want to start the numbering. So in the first example, we just use the NL fruits.txt, and it's going to put a number by each of them. In the second example here, if you use the -n and ln, you're going to left align the numbers. Next tool we're going to talk about is sort, and then we'll just slightly reference shuff as it pertains to this. So the sort command is going to arrange lines of text according to some chosen ordering that you give it to it. It's really good for organizing and cleaning data. By default, it performs lexicographical or alphabetical sort. And what that means, it's going to, if you don't know, I'm sure you already do, but it's going to read from left to right. So as you can imagine, this might do funny things with numbers. But let's look at a simple example first. Oh, the other thing I want to mention is that you have to, in Unix, uppercase and lowercase are always a consideration. So if you want to ensure that it's always going to behave the exact same way, you can use this export command, lc_all = C, and that means that all the tools that are going to be using this will always stick the capitals before the lowercase. So in this example, we have unsorted text, with a bunch of fruits in it. If we use sort without setting that, again, depending on the system you're on, the export, it might be the default, but it might not. So if we sort unsorted.txt on some, we'll get apple, banana based on where the capitalization is not considered. If we use this, then we know that we're going to get capitals first and then the lowercase. So this tool will also allow you to sort based on the columns. So the format that the column delimiter comes in is that this -k 3,3. So that this example says we want to sort on only the third column. It's a little funny looking, but what it basically says, use only field 3 to sort this. You could also do things like -k 2,3, and what that's going to do is it's going to kind of munge those two columns together and use the entire column as one entity. So it's going to read from right to left, and it's going to keep reading through the two columns. Similarly, if you just put K2 in there, it's going to take it from the second column all the way to the end, regardless of how many columns it happens to have. So in our first example, there's K33, so we're just we're sorting on this third column. In the second one, we're going to sort based on the second column. Notice that the second column is numeric, but it doesn't know that. So it's basing it, it's evaluating based that they're just characters. So 12 and 35 are going to come before 6. If we wanted to consider that it's a number and evaluate it as such as a continuous value, then we need to designate specifically that it's a number by adding the dash n here. Note that the dash n could be either after the first number 2 or after the second number 2. It doesn't matter. So here we're just pointing out the difference between using ensuring that it's evaluated as a numeric value versus a character. So the other thing we can do is we can, in some cases, we don't want to list everything because it's too much information. We want to limit our output so that we just get one instance of things that are inside there. So the title here is restricting listing to unique values is a little misleading because it's not going to just list unique values that are coming from the input, but it's going to create a list of unique values rather. In addition, we can sort by multiple text files. So if you're familiar with Excel, when you do the filter, you can filter on first one and then all the different lines. This does the same thing. Again, the nice part here is we can do it in one line and never have to open the file. So in this case, we're ordering first by column 3, then by column 1 or field 1, and then by field 2. We can also list in reverse order by using the R. Again, it doesn't matter if you have it after the first field number or the second field number. You can also include the numeric in when you use multiples. Another sometimes useful command is the shuffle command. So if you want to have, if you essentially you want to unsort your data, you can use the sort -r command to unsort your data. However, when it sorts it, it's going to group like entities together. And sometimes this isn't what we're looking for. What we really want is a random, the numbers to be randomized, or the characters to be randomized, or the entries to be randomized. So in this case, we can use the shuff command. So a little bit more on a tangent, but if you happen to want to create a sequence of random numbers, then you can use the seek command and the shuff command to randomize your numbers. Anyone who's taken kind of a intro to computer programming class knows that you always have to create some sort of random number file. So this is a useful one. The next command we're going to talk about is split. So split is going to take a large file and break it up into smaller pieces. A thing to take into consideration that the split file in and of itself doesn't interpret the content at all, so it doesn't make smart decisions. It does exactly what you tell it to do. So by default, the split command is going to split things into 100 lines. And when the lines are designated by things that end in a carriage return or \n. So in this example, we have a file named genome.fasta, and we're going to split it. So what it's going to do is it's going to split it into as many files as it has. It will give each file up to 1,000. And if they can't be divided evenly, the last file is going to get whatever's left. So the word count or the WC command here is just to kind of show what's coming out. So WC stands for word count. The -L stands for line. And star is indicating that we're going to get the number of lines per all the files that are in this current directory. So our initial file, genome.fasta, has 9,991 lines in it. So for our first 9, they're each going to get 1,000, and our last one is only going to get 991. However, you can imagine that sometimes 1,000 is not the files you want. So we can use the -L command to change how many lines we get. We can also, by default, it creates these kind of generic names, XAA, XAB, XAC. While this is nice, if we ever come back to it, it could be that we have no idea what these files are for. So we're probably going to want to create a prefix to those that is more meaningful. So we can do that by adding at the end of the command a prefix that we want to use. That prefix is going to be substituted for the X in the previous one. So just a little bit of thought why we might want to use split. Sometimes files are, when they're really big, it's hard to move them to different systems. And it's also sometimes we want to split up our data in order to run applications in chunks. And so we need to reduce the size of them. So in some cases, I mentioned before that that split doesn't really consider what's in the file. It just splits based on a carriage return. However, in many cases, we're going to want to be able to define what we consider a line. And so in some cases, we might want several lines to be considered a line. So we want it to start with something. And we can do this by, so here's an example of one. So in the genome, basically, the first line kind of designates what it is, and then it's followed by a series of the sequence, the data sequence. But you'll see that if we just split it kind of without any thought behind it, we'll get the first line that says that it's a mouse, but then we'll get the next 2 lines which should be associated with the mouse. The genome sequence should be associated with the mouse, but now it's a different line. So what could happen is that we split sequences apart, and so that doesn't really make sense. So we need a tool to make the split smarter. We do that by using the -T. Basically, the -T indicates how we want to define what a line is, and the -T is where the line starts. In this case, we're going to use the capital or the greater than sign. So in this example, it splits them up. However, you'll notice that, so before the line ended with a \n, and you'll notice that in the previous examples, it didn't add that into the field. So it makes the assumption that you don't want it. So you can see in the first 3 files that the first one has the greater than sign in there, but the next 2 don't have it. So at the very end in one of our workflow examples, I'm going to show you how to fix that. The next tool we're going to talk about is grep. Grep stands for Global Regular Expression Print. And the purpose of it is to search for text that matches a pattern and then prints out the matching lines. We are going to use kind of simplified logic in here. This says using regular expressions. We are going to use kind of literal strings as our regular expressions right now, and that's kind of the simplest regular expression. We have an entire presentation on regular expressions. I strongly encourage you to attend that because it'll allow you to make more sophisticated or use these in a more sophisticated way. So again, Unix is very, very case sensitive. So if we want to search for banana all lowercase, if we type banana all lowercase, it will only look for that string in that case order. If we want to have capital, then we can use the capital banana. If we don't care of uppercase or lowercase in any of the character fields, then we can use the -I, which makes it case insensitive. So there's different ways to get our output. If you are exploring and you want to have a little assistance to help you identify what you're searching for, you can use this alias command. So if you alias grep into grep -- color auto, it's going to highlight or it will colorize the match that you're looking for. In some cases, when we grep for things, we don't want the entire line, but we're only going to want the individual, what we're searching for, to be returned. And we can do that with the -O command. A very nice feature of grep is that it allows you to not only print out the line that you searched for, but it also allows you to print out the lines before and after. This is really useful for in a couple scenarios. First, if in log files, if you're looking at errors, usually the error is important, but it might be what happened beforehand that is more important. Also in like time series data, there will be an incident and you want to know what happened directly before that incident and directly after that incident. So by using the capital B option and the capital A options, you can designate the number of lines before the matching line and the number of lines after the matching line. You can also use them both in the same line. So if we do grep -B space the number 3 space -A space the number 2 /kumquat, it will list them the 3 lines before and the 2 lines after all in the same command. So up until now, you'll notice that I was grepping on one very specific file. And so we were only getting out the lines of the file because we already knew which file the response was coming from. But we can also search many files by using the star command. So if we grep for line in star, it will tell us not only the file it came from, but provide us the line that it was in. So in some cases, we want to look, we know what we're looking for. We don't know what we're not looking for. So, and the not looking for might be more important because it will indicate a problem or something. So we can search, like do an inverted search. So we want to find everything that doesn't have lime in it, which could be more interesting. And we do this with the -V option. Other things that we can do is we can print the number of lines. Sometimes we don't care. Well, we're searching for a line, so we know returning the line isn't all that informative to us, and then we would have to count the lines if we want to do that. We can use the -C option, so it will return exactly how many times something occurred. In addition, sometimes we just want to know the file that something is in. So we can use the -L option, grep for kumquat, and it'll return a list of all the files that kumquat is in. If we use the -L, it will return a list of all the files that kumquat is not in. As I mentioned, grep stands for Global Regular Expression Print. So we can create much, much, much more sophisticated searches than what we're doing. I'm not going to go into too much detail, but I will give 2 kind of nice examples that are pretty common and not too complex. So if I want to grep for pair in a file, it will return all the pairs. If I instead want to grep only for pair when the line starts with pair, or if I want to return the line only if the line starts with pair, then I can use this caret option. So regardless of if pair is in it anywhere else, it is only going to return those two lines where pair starts it. Similarly, we can use the anchor $ at the end of the string that we're searching for, and this indicates that I only want to look for instances where my string is at the very end of the line. The next tool we're going to talk about is SED, and SED stands for Stream Editor. The next two tools I'm going to talk about, SED and awk, are actually pretty sophisticated tools, and there are entire books dedicated to this. When I first started in school, I took an entire class, and we spent an entire quarter playing with SED and awk. So what we're going to touch on today is only going to scratch the surface. So if you want to go into more depth, here are some resources that you can look at specifically for SED. So SED stands for Stream Editor. What it does is it reads text line by line, and then it's going to apply commands and output those results. So in this example, the really nice thing is we can manipulate files without ever opening the files. Things that it does very well is it can do search and replace, it can delete lines, it can insert or append text, it can transfer characters, it can also extract specific parts of a file. So kind of the format that it's in is you'll invoke the command by the SED, by typing in SED in the command line. And then between the quotes is going to be what you're looking for and what you want to replace. And the first letter there is S, which stands for substitute. So within the first forward slashes, you can have a string. So it's going to search for that first string. And then the next forward slashes, you can replace it with whatever is there. Now, by default, it's only going to do the first occurrence in a string that it happens. So if it happens anywhere in file, but it happens multiple times, it's only going to apply this once to that line. If you want it to be applied to every occurrence in that line, you can use the -G at the end, which stands for global. In addition, you can use SED to search for a pattern and then only do a substitution on the lines that have that certain pattern. And this is the format that it'll be. So let's look at some examples. So in the first one, we are going to search for pair and we're going to replace it with X. In this example, it's searching for the first occurrence of pair, wherever pair may happen to be in the line. In the second one, we want to make sure that every single pair in the file gets substituted with the XXXX. So we include the G at the end, which again stands for global. So we're gonna look at kind of those simple anchors again. If we only want to replace instances where pair starts out the line, then we can use the caret at the beginning. Similar, if we want to only replace pair if it completes the line, then we can use the $ right after it. So you can restrict the transformations to lines that only contain a specific pattern. So in the top one, we're going to do it globally on every occurrence that happens. So every time we see pair, we replace it with orange. But what if we don't want to do it on every single line, but we only want to do it on lines where grep appears? Grep can appear anywhere in the line, but we can still replace pair or orange regardless if it occurs before or after. By default, SED prints out every single line it processes, but in some cases, we don't want to print them all out. So we can use the -N command. And what the -N command means is print nothing, unless you specifically tell it to print something. So in this first example, we're telling it print nothing but line 5. In the second one, we can ask it to print like a range of lines. So we're asking it to print lines 3 through 5. And the third one, it allows us to indicate where we want to start, similar to the above. So we want to start at 2, and then we want to print every third line. Said, like all the other commands that we have, write to standard out, but sometimes, and with all these tools, one of the nice things is that it does go to standard out. You can do a lot of debugging before you commit yourself to anything. So with these commands, you can write it goes, you run the command, it'll print it to standard out. Once you get content that you have actually created the correct command so that it's going to do exactly what you want, you can write the results to a specific file. But since SED is a stream editor, it does everything line by line. So if you were to have it take some action and you want to overwrite the file, you can't do that because the file is still open and still working on it. So there's two ways you can handle this. You can either put the output to a temporary file and then copy that temporary file to the main file after your job is complete, or you can modify it in place by using the -i command. And that means it's going to go through, and as it does each line, it's going to modify it in place. The next command and the last command we're going to talk about is awk. And awk is actually a pretty powerful tool. It's actually a text processing language. It's not even just a tool, it's a text processing language. And it specifically works with like structured data, especially kind of where data is organized into columns. Again, we could spend a whole hour on this. We could spend a whole week on this. We could spend a whole quarter on this. So here are some additional resources where you can look further on into it. I will touch on the basics and hopefully get you excited to learn more about this tool. So the other thing that's nice again to make things efficient for you, basically awk is a programming language that comes with your shell, so you don't have to import any tools to use this. The way awk works is it consists of one or more rules that contain a pattern and then an action on it. You can execute them again by invoking the awk command, by typing awk, and then within single quotes, you'll have the pattern, and then the actions you want to take will be in squiggly lines. You can have multiple actions take place, and all of them will be in those squiggly lines. You can have multiple actions happen, and they will be combined with semicolons. The other thing is, as it's a programming language, you can do math with it. You can do, it has built-in variables. You can assign variables. Basically anything you can do with a regular programming language. This it's not quite as sophisticated as some other ones, so you might want to not do complicated programs with it, but you can handle most anything with it. And as with the programming language, you can do formatted output. You can also indicate that some things should happen at the beginning and some things should happen at the end with the begin and end code words. So the most common use of awk is to print selected fields from each line of a file. Awk, like said, processes files one line at a time, and it splits the fields based on white space. You can reference these fields by their position using the $sign, so $1, $2. It also has a built-in variable, NF, which stands for number of fields. So in the example we have here, we have a people.txt file. The cat command just shows us what's in that file without having to open the file. We have actually the name of the people who work on or on the complex team, followed by their favorite pet, a savory meal, their favorite fruit, and their favorite color. Now, for awk, we can just print the certain fields that we are interested in. So in this example, we print the first field, the third field, and the last field. So NF by itself just states the number of fields. By adding the $ in front of it, we're indicating that we want to use it as a variable. So the NF is really useful if you don't know the number of fields you're working with. So if you have what we call ragged data, if we want to print, but if you know that the final field will always have the information that you want. So for example, if you have an input field and they give the first name, last name, various things, but how it's incorporated and put into a file, the names that are blank don't actually contain anything, and so they become shortened. But you know the one field that was required was the last field, which happened to be like an email address. So if you just want that last field, you can use awk print NF, and it will respond and give you just that field. Now, if you print NF, it will instead print the number of fields that are in a given line. So if you avoid using the $. Awk can also, you can do formatted text in a couple of ways. One of them is to actually add it into your output. You can add it in by putting it in double quotes in the middle of your print statement. Note that everything within those double quotes is going to be used and nothing more, nothing less. So if you had the quotes just around favorite food is and didn't have the extra white space, the response would be Bob and favorite would be slammed into Bob and favorite would be one word, and is meatloaf would be one word. So it's important to include those spaces. Again, you can use awk by searching for certain lines to apply it to. If we only care about people who like pizza, then we can search for pizza and then just print the first and the third columns. awk uses white space as the limiter, but as you can imagine, sometimes this is not how we get data. A very common way for us to get our data nowadays is to have comma separated values. So if we want to change what the delimiter is, we can use the -f command and designate what our delimiter is going to be after that. So again, this is kind of squishing all the things together. We initiate the command, and before the single quote, we designate what is going to be considered our delimiter, and then we put the action that we want to take on it. So we want to print the first column, followed by a space state bird is, followed by the third column. I think I mentioned that it is a full-fledged programming language, so we can do math, we can do square roots, we can do log, we can do exponentials, we can do trigonomic functions, we can do random numbers. And we can do kind of these series of commands. So for awk, if we want to sum the rows together, we can use sum equals 1 plus 2, and we are then initiating, or we are creating a variable there. We can do the product of columns 1 and 2. Then we can print what the initial value of 1 is and the initial value of 2 is, and then the sum and the product. Similarly, we can use sine, cosine, log, square root. In some cases, we want things to happen just at the beginning or the end of beginning or end of our, let's say, program. And so to do that, we just use the keywords begin and end. So in this example, we want to make sure that we have a header, and we want to initialize a variable before we start our actual calculations. So we use awk in the single quotes begin. Then the action will be in squigglies. Note that all the actions are separated by semicolons. Another neat feature, which makes it a little easier to read if you're doing this all command line, is that your commands can be broken across multiple lines. Again, when it starts to get complicated like this, it might be best to create a bash script. But before you want to create a bash script, you can do this here, because again, this will help you debug and put everything in order before you commit to anything. So awk also allows you to do C-style formatting, so you can use printf statements to print things. In this example of printf, we are doing floating points that have 4 characters, 1 decimal point for the first 2, 7 characters, 4 decimal points in the second one, and the \n to do a carriage return at the end. So in the previous slide, or 2 previous slides, I'm not sure, we saw that we could sum across rows, but awk also lets us sum across down columns. So to do this, we use the += sign. So in this example, we sum the first column, we sum the second column. We also can use another predefined variable, nr, which stands for number of rows, to find the average of those columns. So we print, we're adding all the columns as we go through. There's 4 columns, you can kind of see they add up, and then at the very end we have the average of those 2 columns. As a programming language, it has variables, it has arrays, it has branching, it allows you to do loops, it allows you to do user-defined functions. But as I mentioned before, there's other programming languages that are easier to handle than this. But the if-then-else statement is still a very useful one. It's kind of still in a small enough range that it's very useful to look at. The format that it is awk in the parentheses, if condition, then do something. Each of the statements are going to, each of the actions are going to be split up by a semicolon. So we'll have 2 examples. So the first one is if the number of fields is greater than 2, then we want to print it. So if we have a bunch of fields and we want to just have what we would assume is complete data, which means that it has more than 2 fields, then we can go to the ragged text, and only the lines that have at least 3 fields are going to be printed. Another example is if you have a bunch of numbers and you want to list them in ascending order, you can use an if statement to do that. So if the first column is greater than the second column, then we want to flip them around and print them in the opposite order. If, however, they're already in ascending order, we want to print them in exactly the order that they already come in. So I gave a lot of information very quickly here. What I strongly encourage is for, if you're interested in going further with this, is to take a moment and download those GitHub repos and test these things out for yourselves. There's 2 options. You can either do things command line, or you can use Jupyter notebooks to walk through them. As you go through them, just doing the exercises that are predefined is great, but if you really want to learn it, we recommend that you take it a little further. So add some errors into it, try to expand it, try and string things together, and then try and use them in your own workflows and how they might be useful to you. So to kind of tie this all together, I want to give a couple examples of how we use these tools in the work we do here at the San Diego Supercomputer Center. So at the San Diego Supercomputer Center, we support users using NSF-based systems. So we have big systems. We purchase them with essentially NSF money. But before the NSF was ever willing to hand off the money to either us or the vendor who sold the product, they want to ensure that the systems are actually doing what they're supposed to do and performing it. So first, that it can handle the calculations it's supposed to do, and that it's performing at a level so that it's as efficient as it's supposed to be. So we run, before the system ever goes into production, we stress the system out and run benchmarks on it to ensure that it's doing everything correctly. So one of the benchmarks that we run on our systems is called HPL, or High Performance LINPACK. And if you were on your desktop system, you could run this once and maybe 4 times, or you do it 100 times, but it might be easy to pull out the numbers by just opening the field. On the systems we have here, there are hundreds of nodes and thousands of cores. So it is not reasonable to consider that we're going to open every file and extract information from them. So having these tools where we can run them and never open the files and write them in scripts to pull stuff out is essential. So what the LINPACK reports is the first line of the output from LINPACK is going to provides us the node that the job ran on. These 3 dots indicates that there's a bunch of other garbage that's in there that's not actually part of the file. But the important stuff that we need to prove to the system is the efficiency, so it's working at the pace that we expect. So we need the time out of it, and we also need to know that the calculation that it did, that the math is correct. So we want to know how many times it passed the test. So what we want to do is without opening all these files, we want to have a report that has them all in one place. Then we can evaluate all the times and see if they're relatively in the same range. And we want to know how many times it passed or how many times it failed. These pass and fails and the times and tied with the node name is really important, because if it didn't pass or if the time is wrong, then we need to go back to that particular node and look for it. So Bob, who developed this thing, is actually our tester for these things, our compliance reliability tester. And so he runs these all the time. So he wrote a script that will evaluate all the files that in a certain directory. So he runs these in a certain directory and creates all the output files in that directory. So it runs all these files, it searches, it uses a tools such as head, grep, awk, and word count, and it creates a report like this, which is really easy to evaluate what's good and what's bad. So let's look in particular at what that code does. So the first line of that code is going to print a header. So it shows the node, the time, and if it passed or failed. And then we're going to go into a for loop, and we're going to list all the files in that directory that are named output.hpl with something following it. And then we're going to use our head command, because we noticed that the node name was the only content. There was only one column in there, and that was the only thing in there. So if we do head -1, we get just the node name from that first line. The time was in a line where it had multiple fields, but we can always designate, or we can always identify that the time is going to be on the line that starts with this WR12R 24R. And so the second thing we're going to do is we're going to search for, using awk, we're going to search for lines that have that string, and we're only going to print the 6th column, and we're going to put that into a variable t. Then we're going to check the number of times it passed and the number of times it failed using the word count. And then we're going to echo that out. So the HPL is pretty much a standard benchmark that has been used for all traditional HPC systems. But nowadays we're kind of in the world of AI. And so there are many more specialized AI hardware systems coming online. So the benchmarks you run need to actually test out that the specialized hardware is working. So we run this BERT test. So it's similar to the previous one. We need to know the number. We need to know if it passed or failed. In addition to knowing the node we're on, we also need to know the specific card that we're on, which is the second line that starts with the 1 there. In this case, this benchmark doesn't give us a specific time of how long it ran, but it tells us the time before it ran and the time after it ran. So we're going to need to do some math here to extract that. Then the other important stuff is that if we're getting correct answers and the time it took to take those. So similarly, in this bash script, we list all the file, for every file that is in the directory that's named out.something, we're going to pull the first line out of it. So the first line here is a little overkill because we noticed in the 2 slides above that the node was the only thing listed in there. However, if you're not sure, you can be specific, and in this case, we are piping the one command into the next command. So we get the first line, and then we print just the first field of that line. The next thing we need to know is we need to know what card we're running on. So we're going to use an awk command, search for a particular string, and then print the fourth field. We need to calculate the time, so we need to pull out the time before and the time after. We're going to pull out the correct answers and the achieved sentences, and then we're going to actually calculate the time using this expression from the end time to the start time, and then we're going to print those all out. And here again, we have a very nice thing where it's very easy for us to evaluate on a glance in one file how all of our nodes are doing and how all the cards on those nodes are behaving. The last example or case study I'm going to give you is something that we used in our split example. So we used what we call as a FAFSA file, and a FAFSA file is a text-based format used for bioinformatics to store DNA, RNA, or protein sequences. And each line, or each entry, again, not each line, but each entry begins with the header line that starts with this greater than character, and it's followed by an identifier or a description, and then the following lines are going to contain the biological sequence of what we see below. So we wanted, what we did before is we split it, and we split it on the greater than character to indicate that that's what our lines are going to be identified as. But what we noticed before is that it was not printing out that character, and again, we need that character in there as an input file. So we wrote a little script that for the file in genome, because again, we split it into genome and something, we're going to use the sed command to substitute wherever SP is at the beginning of the file and substitute it with the greater than SP. Again, we could either use the -I here so that it gets done in place, or we can redirect the output to a temporary file and then move that temporary file into the initial file once it's done. So let's talk briefly about using LLMs. I initially was hesitant about LLMs, but I am a strong proponent of making your life easier. As we mentioned in the beginning, if tools are there, you should use them because it makes things better. Because they're there, you can use them. However, LLMs will give you back exactly what you ask for. So it's really important for you to know what you're asking for and to have some background to understand that what it's printing back at you, if it makes sense and if it's actually going to give you what you want. So here's just a little example. There's a couple examples here. What's nice about, at least in ChatGPT, I think I use Copilot a lot, is that sometimes it will give you an output and then it gives you a really nice explanation. I should mention that on any Unix system, if you want information about any of these tools, you can use the man command, so man space the tool name, and it'll give you how to use the tool and all the parameters that are available with it. So in conclusion, Linux provides lots of tools out there. But there's many for text manipulation. We only scratched on several of them, but the ones that we did touch on today will allow you to do many things. Strongly encourage you to test these out. As you're going through, you're going to run into bobbles, but every time you make a mistake, you can see that as you learned something because you learned what you did wrong. And again, we have two other presentations that I highly recommend. So these, as the tools are and what we provided today, can be very useful. But again, learning how to use them in bash scripts and being able to take advantage of regular expressions within them makes them really powerful tools.